I'd like to welcome everybody to this special panel that we have today on innovation in oncology. When things don't work in oncology, and they still very often don't work the way we want them to work, people are asking again and again, what could we fix? What could we change? How could we accelerate it? I don't think there's ever been a period that has seen this much innovation in any scientific area as we are seeing today in oncology. It's driven by tremendous need, to be sure, but it's also driven by tremendous scientific opportunities that have been laid out by decades of work understanding the actual basis of cancer that are finally paying enormous dividends. So the Biden Cancer Initiative is organized backgrounders on important topics, and this is the backgrounder on innovation in oncology. And we are lucky enough to have today 5 amazing speakers, all of whom are very active in entirely different areas, to tell you a little bit about what they do. So our third speaker is Professor Paula Hammond, who is the David Koch Professor in engineering and is the head of the Department of Chemical Engineering at MIT. And she originally had no intention of going into chemical engineering whatsoever. She grew up in Detroit, the Motor City, and she was planning to write children's books. But at the last minute, she was deterred from a career in children's literature by a high school science teacher, a chemistry teacher in the junior year of high school, who got her hooked on the amazing nature of chemistry and chemical engineering. And she has made it her career, and she is now applying it to innovation in oncology. So, Professor Hammond, great to have you.
Thank you. I'm very excited to talk to you today. I'm going to try and describe how nanotechnology can help us deliver drugs safely and more specifically to tumors. But before I do that, I know that a number of people have heard about nanotechnology and understand what the scale is, but I thought it would be good just to remind everyone of how small nano is. If you can imagine taking a singular human hair and then laying it up lengthwise and slicing it along the length 10,000 times, that singular slice would be about the size of a single nanometer. So that hopefully gives you an idea of the size of a nanometer. And the systems that are being designed right now to address cancer are in the range of tens to a couple hundred nanometers. Now, it turns out that nanotechnology can be extremely helpful in packaging drugs. And in fact, in our own laboratory, we've been designing nanoparticles that can contain a drug within a core. That core can hold a very traditional drug, a chemotherapy drug that we all know and trust, like doxorubicin, which is also known as Doxil. And it can be contained in a familiar container, liposomes, which are formed from natural lipids, or polymeric particles that can degrade. But what we can do with that nanoparticle is wrap around it a series of different material systems, which include molecules, siRNA, that can silence the genes that allow a number of tumors to be resistant to these chemotherapy drugs. Finally, we can wrap on the outside, shown here as a green layer, a singular layer that allows us to take on a stealth property. Now, the reason that we're doing this is that we're designing this nanoparticle to be small enough to enter the bloodstream and ultimately to find its way to a tumor. In fact, on this scale that's shown here, we're going to design a nanoparticle that is a little bit larger than a virus. So it's going to be able to get into the kinds of places that viruses can get into. But that outer layer is going to be something that's going to allow it to be in the bloodstream without being recognized as if it were a virus. Because if it's recognized, that will elicit our immune system to get rid of it. So instead, we're going to use a polymer, a large molecule that is going to essentially mimic the behavior of something that would naturally be in the bloodstream. In fact, we choose polymers that are highly hydrated so that they have this strong negative charge and also a cloud of water molecules that are bound to that outer layer. It gives us a kind of stealth behavior for the nanoparticle, or some might think of it as a kind of invisibility cloak. Now, to be able to do this, we need to be able to use the physical chemistry and engineering skills that we develop in our own laboratory, but we also have to be able to work with biologists who can help us understand the mechanisms by which these tumor cells avoid cancer cell death in the presence of chemotherapy drugs, so that we can use siRNA, this silencing molecule, to silence those genes. And we also have to work with clinicians who will help us to understand how to best deliver these systems in the body. Now, these nanoparticles can be constructed layer by layer using a very simple process of alternating charge. And this is how we use physical chemistry and chemical concepts to actually address cancer. We can actually use the fact that positive and negative attract to layer, essentially shrink wrap these nanoparticles with first something that's positively charged and then something that's negatively charged. In fact, we can think of this as a highly structured nanoparticle in which we can incorporate the drug, siRNA in our case, which is negatively charged, within polymers that are positively charged and will allow us to release that drug. We can, in fact, think of it as a kind of Wonka gobstopper of cancer delivery, where we have these multiple layers that can ultimately either melt away, releasing drugs one at a time, or swell and release the drugs with differences in the rates at which they get out of those layers. And ultimately, the idea is to get these nanoparticles into cells. Now, the reason that we're using something that is nano-sized is multifold, and one of them includes the fact that a number of tumors may grow so rapidly that their blood vessels are defective and they have leaks in them that are about the size of nanometers. In that case, we can then inject these nanoparticles into the bloodstream. They will circulate. Over a period of time, they will begin to accumulate in the tumor through these leaks. And I often describe this as something of the pinball machine effect, where you have a nanoparticle that makes its way in, finds its time throughout the tumor before it has a way to get back out again. That gives us a long residence time in the tumor, and that gives us time to allow the nanoparticle to be taken up by tumor cells. However, it turns out that not all tumors have leaky vasculature, and we have to find other ways to get into these tumors. And this means being able to design material systems that can penetrate tumors by engaging endothelial cells. These are the cells that line the blood vessels of tumors, or through the penetration of the tumor tissue. Once they're inside the tumor tissue, we want them to be taken up by tumor cells. And it turns out that we can design these nanoparticles so that they're actually responsive to the tumor microenvironment. One way in which we can do this is by using the fact that often tumors are slightly acidic. They have a slightly lower pH than the pH of our bloodstream. It turns out that our layered nanoparticles actually change when we undergo a change in pH. And we can therefore design them so that when they get into tumors, they go from this stealth mode to a much more sticky mode in which they engage with a large number of other cells simply due to the fact that they're presenting positive charge now. And once they begin to engage with that cell membrane, they can get taken up into the cell. And once they're in the cell, they get even more acidic and they begin to release their cargo. For example, we can actually see nanoparticles that can accumulate in sections of tumor, even though we've injected them through the tail vein. Now, the simple idea then is to create clever combinations of drugs. And in our case, we can look at siRNA that can silence a number of the genes that are responsible for tumors' aberrant behavior. One of these is actually a protein that sits at the membrane of the tumor cell and pumps out the chemotherapy drug before it can actually reach the nucleus and do its damage. This is called MRP1, and this simple pump actually spits the drug out rapidly before it can actually have any effect. If anyone has ever fed a small baby, they know that this is a very familiar phenomenon in which the nutrition that is going in never makes it in. Now, this kind of MRP1 pump can be silenced, and we actually did this in a very simple animal model in which we have tumors on the backs of mice, and we can see that these tumors grow very rapidly at the top, these control animals. If we just deliver the doxorubicin alone, then we get somewhat of a decrease in the rate at which these tumors grow. And finally, if we deliver the combination in which the siRNA comes out first, followed by the doxorubicin, we can actually see that the tumors are getting smaller. And this is a sign of regression. Now we're very excited about this approach, and we're beginning to use combination therapies in these nanoparticles. What it enables is a way to deliver a clever combination of drugs. What it uses is what we learn from data science and from clinical approaches to personalized medicine, and we're very excited about the fact that we can now use this in a number of other tumor types, including lung cancer and ovarian cancer. Thank you.